So the first topic that I want to discuss in this course is extremal graph theory. And in particular, there's a whole class of problems which have to do with what happens if you forbid a specific subgraph. Forbid a specific subgraph and ask you what's the maximum number of edges that can appear in your graph. In particular, and this is the question that we saw at the end of last lecture, which now we're going to present as a theorem, Mantel's theorem, essentially asks if you know that your graph has no triangles, what's the maximum number of edges it can have? And Mantel's theorem tells us that the extremal example is when your graph consists of putting half the vertices on one side, half the vertices on the other side, and putting in all the edges between the two sides. Okay, so this is a complete bipartite graph. For these partitions, we denote complete bipartite graphs like that. Okay, and Mantel's theorem tells us that this graph among triangle-free graphs has the most number of edges. Triangle-free graph on n vertices has at most, okay, so the number of edges there is n squared divided by 4, round down, that many edges. And from this example, this bound is tight. Okay, so Mantel's theorem gives us a completely satisfactory answer to the question of what's the maximum number of edges in a graph without triangles. And I want to begin by showing you a few different proofs of Mantel's theorem. Okay, so with illustrating some different techniques in graph theory. So we'll see quite a few proofs in today's lecture. The first one begins, well, here's the setup. I have G, an n-vertex graph, and let me denote the vertices and edges of G by V and E. If I have an edge in G between vertices X and Y, then note that they cannot have any common neighbors. Because if they did, I would see a triangle. Okay, so I assume G is triangle free. So what can we say about the degrees of the two endpoints of this edge? Well, they cannot add up to more than n. Right? So in particular, so exactly, so the degrees of these two endpoints is at most n whenever xy is an edge. So here I'm using d to denote degree. Well, okay, so now let me consider the quantity which is the sum of the squared degrees. On one hand, I claim that this sum is equal to this quantity here, where I sum over all edges. And the reason is, well, look at the sum. Suppose, imagine writing out all the summands. How many times does each dx come up? So each dx appears 1 for each edge x is in, so appears exactly dx times. But we saw from up here that each summand is at most n, so this sum here is at most mn. On the other hand, let's consider the quantity which is just the sum of the degrees. Okay, and you know, sometimes known as the handshaking lemma, that the sums of degrees is just twice the number of edges. Each edge is considered twice in the sum. Well, now we apply the Cauchy-Schwarz inequality, which, as you'll see many times in this course, although you might think of it as a fairly simple inequality, it's extremely powerful. And it will come up pretty much throughout this course. By the Cauchy-Schwarz inequality, compare these two quantities, I find that we have this inequality over here relating the sums of the degrees and square of the sum of the degrees. But we saw, on one hand, the left-hand side is 4m squared, and we also saw that the right-hand side is at most n squared. Putting them together, we see that m is at most n squared over 4. And of course, because it's an integer, it's at most the floor of this number. Okay? And that's a proof of Mantel's theorem. What can you tell me about the equality case in this proof? Okay, so I'll let you think about that. But let me show you some other proofs. In other words, are there graphs with the same number of edges as the graph shown up there that is also triangle-free? Is that a unique example? Okay, so let me show you a different proof of Mantel's theorem. In this proof, so we begin with a step that seems a little tricky. Right? Let's let A be a subset of vertices such that A is a largest independent set. Of G. Okay, so remember, independent set is a subset of vertices with no edges inside. It may have many independent sets, all having the same maximum size. Take one of them. Right, so why should you do this step? Well, sometimes magic happens. Let's consider some vertex. Right, so consider some vertex, let's say x, and look at its neighborhood. The neighborhood must be an independent set. Otherwise, I get a triangle. So every neighborhood is an independent set. And as a result, the degree of every vertex is at most the size of the largest independent set. Okay, so now let B be the complement of A. So I have this A and B. Every edge has to intersect B. Right? The edge cannot be entirely containing A because A has no edges. So the number of edges of G is at most, well, I count over the vertices in B, the degree. So maybe I overcount. Right? So the edges containing B, I count twice, but that's okay. So this is an upper bound on the number of edges. But I also know that every vertex in the graph has degree at most the size of A. So each summon is at most the size of A, and I have B terms. Okay, so I have that. Now, by the AMGM inequality. We have that. And the sizes of A and B add up to the entire vertex set. So n squared over 4. Okay, so that gives you another proof of Mantel's theorem. What does this proof tell us about the equality case? Now, something I always want you to keep in mind when we do proofs is, especially if we have a tight example like that. And later on in the course, we'll almost never have good examples like that. And so this is still early on in the course, we're still very clean examples, is to keep the extremo example in mind. And every step in your proof, it should be tight for that example. Otherwise, something went wrong with your proof. Now, let's think about the inequalities. At equality, we must have that, okay, so looking at this inequality, so there are no edges in B. Okay. We also have that, okay, so by that, so every vertex in B is complete to A. And finally, A and B should have the same size. So it is exactly the configuration shown up there. Now, when n is odd, we're rounding down by 1. So you can lose a little bit, and then you can check that actually what we described up there is also the unique example. Okay, so that graph, the complete bipartite graph with 2 equal parts, is the unique maximal example. Number of edges in the triangle-free graph. Okay, great. So once we know what the answer is for triangle-free, of course, we should ask further questions. Instead of forbidding a triangle, what if we forbid other graphs? Okay, so, and what are some natural next steps to take? Well, so instead of triangles, we can ask, what about if we forbid a K4, a clique on 4 vertices? Or, in general, what if we forbid a clique on a fixed number of vertices? So what is the maximum number of edges in a K R plus 1 free? There's a good reason why I indexed R plus 1 graph and vertices. So, for example, if we're interested in K4 free, so what might be a good candidate for a graph with lots of edges that has no K4s? I mean, certainly that example we saw, it does not have K4s because it doesn't have any triangles, but we can do even better. Okay. Instead of taking 2 parts, you can take more parts. Well, for K4, if I take 3 parts, each with n over 3 number of vertices, of course, if n is not divisible by 3, round up and round down, and putting all the edges between different parts, you can see this graph here has no K4. Okay, so that's an example of a K4-free graph. Well, does it have the maximum possible number of edges? Okay, so is this the best that we can do? So it turns out the answer is yes. And that's the next theorem that we'll see. But just to give it a name, so we're going to call graphs like these Turán graphs, because the next theorem is proved by Turán's theorem. So a Turán graph, which will denote T sub n r, it is a complete R-partite graph such that there are n vertices whose part sizes are all nearly the same, up to at most 1 difference. Right? So this is an example here. but in general, maybe you have R parts, and I put in all the edges between different parts. All right, so it's not too hard to calculate the number of edges in such a graph. And Turán's theorem tells us that that is the extremo example. You cannot do better in terms of getting more edges. So if G is an n vertex, K sub R plus 1 free graph, then it has at most the number of edges of the Turán graph. All right. It's a generalization of Mantel's theorem, and you can think about if the proofs that we did for Mantel's theorem generalizes to Turán's theorem. And it's actually not entirely clear how to do it. So let me present for you 3 different proofs of Turán's theorem. Okay, so some of them you can think about, are they related to the proofs of Mantel's theorem that we did? And they all are going to look somewhat different, but maybe superficially. Okay. The first proof, we will use induction on the number of vertices. So actually, this is one of very few times in this course where we will see induction. So of course, induction is a powerful technique in combinatorics, but for almost the rest of the course, we're not going to have clean examples. And when we don't have clean examples to work with, somehow increasing n by 1 doesn't buy you all that much. Here, there are very clean examples, very clean answers, and induction works out quite well. When n is small, of course, you should always address that. You can come up with many funny proofs if you don't address when n is small. So when n is small, this problem is basically trivial. Right? If n is the most r, well, you can have the complete graph on r vertices, and then we're good. So let's assume that we're not in this case. And also by induction hypothesis, let's assume that it is true for all graphs on fewer than n vertices. And let G be a graph that is K sub R plus 1 free on n vertices. And also, let's assume a maximum example to begin with. So let's assume that the G that you chose has already the maximum possible number of edges. Okay, so there are only finitely such examples, so pick one that already has the maximum number of edges. And let's think about what properties this graph G has. I claim that G must already contain a clique on R vertices. So think about that. If G does not contain a clique on R vertices, then I can add in more edges. And I can still maintain the property of being K sub R plus 1 free. So I can assume that G must contain a K sub R. So let's look at one of these K sub R's. So let A be the vertices of some R clique in G. So we have some A. And the complement set, let me call that B. look at the vertex in B. How many neighbors can it have in A? It cannot be complete to A, otherwise I would have an R+1 clique. And so every vertex in B has at most R-1 neighbors in A. So let's count all the edges. The number of edges in G is at most, well, first we should account for the edges inside A, and there are choose 2 of them. And then the edges between A and B. For every vertex in B, there are at most R-1 vertices going to A for each vertex in B. And finally, the edge set of B. Okay. Well, we can say something more about these quantities. We know that the size of B is exactly n minus r. But what can we say about the number of edges in B? We can use induction hypothesis. Right? So B is also R+1 clique free. So the number of edges is at most the number of edges in the corresponding Turán graph. Now at this point, you can do a calculation. Well, I mean, you should expect that the answer we're looking for is, this should be equal to the number of edges in the Turán graph. So you can either just do a calculation to figure this out, or remember what I said earlier, that keep the tight example in mind, and everything should check out for the tight example. Right, so in particular, if you are in the situation of a complete multipartite graph with equal size or nearly equal size parts, what is A? Okay, so A is one vertex from each part. Okay, so you take out one vertex from each part and read off this calculation for this graph over here. And then you see that that is indeed equality. Okay, so you should check out. You don't need to do any actual calculations. Okay. Great. Any questions about the proofs we've done so far? All right. Let me show you another proof of Turán's theorem. So this proof is, has a name. So it's called Zhao symmetrization. So Zhao has the unfortunate honor of having a name that's hard to beat in terms of alphabetical ordering. I think if he and I were to write a paper, I wouldn't be the last author. Okay, so what's this about? So let G be the graph. Again, as before, we're going to take a maximal example. So be the n-vertex graph that is free of cliques on R+1 vertices and has already the maximum number of edges. So here's a property I want to prove about this graph. I claim that if you look at the complement of the graph, of this extremo example, it must be an equivalence relation. Okay, so more precisely, I claim that if xy is a non-edge and yz is a non-edge, then xz must also be a non-edge. So in other words, non-edges form equivalence relation. And again, you should always think about the extremo example. And it is true for the extremo example because the complement are a bunch of cliques, so it is an equivalence relation. Okay, so let's prove this claim. So let's assume that the conclusion is not true. So suppose, for the contrary, that we have xy and yz being non-edges, but xz is an edge. So let's think about what happens to the degrees of non-adjacent vertices. So I claim that if the degree of y were smaller than the degree of x, then I can do something to the graph that violates the maximality of the number of edges. Namely, I can replace y by a clone of x. So I chop off y from the graph, and I look at x, and I clone it. So cloning it means taking some x prime and adjoin x prime to all the same neighbors as x. So clone x into some other vertex x prime. Now, when you do this, I claim that you also get a graph that is free of k sub r plus 1. So we also obtain a k sub r plus 1 free graph. Okay, so why is that? So if you were to have an r plus 1 clique, well, it shouldn't have both x and x clone because there's no edge between them. So it only has one of x and x cloned. But then that would have been a clique in the original graph. However, what about the number of edges that we obtain after this transformation? Well, if x had more outgoing edges, had higher degree than y, then cloning x to replace y increases the number of edges. We obtain a graph that is also k sub r plus 1 free and has more edges than g, which is not possible because we assume that g started with a maximum number of edges. Right, so therefore, the degree of y is at most the degree of x, basically for every non-edge xy. Likewise, we also have that there's no edge between y and z. So the degree of y is, so thus the degree of y is at least the degree of x, and also the degree of y is at least the degree of z. Now, y has a lot of outgoing edges. So now let's replace both x and z by clones of y. As before, we obtain some graph that we'll call G prime. And G prime, same reason as before, is k sub r plus 1 free. Right? If we had a k sub r plus 1, then the same clique should have shown up in G. So G prime does not have r plus 1 cliques either. But what about the number of edges in G prime? So the number of edges in G prime, well, we started with G. We deleted X and Z. Right? So we deleted this many edges. Now, here we're crucially using the fact that there is an edge between X and Z. But now we also added back in a bunch of edges coming from the clone of Y, and there are 2 times dy edges added back in. And you see, because Y has degree at least that of both X and Z, we obtain that this number of edges is strictly bigger than that of G, which contradicts the maximality of G. Okay. So at this point, we know that the complement of G must be an equivalence relation. So the complement is a bunch of cliques. And that's a lot of information, right? So that's almost the best thing we can hope for is a structural information. We're not quite done yet. And why is that? Oh, we're almost there. But we're not quite done yet. Okay, so we need to figure out the sizes of the individual parts. Right, so we need to figure out the sizes of the individual parts. And also note that you cannot have too many parts. Right, so at this point, after the claim, we know that G is a complete multipartite graph it has at most R parts. If it had R plus 1 parts, I would see a clique in R plus 1 vertices. And finally, I need to show, the rest is fairly routine. I need to show what the part sizes have to be to maximize the number of edges. And basically, if you had some 2 parts, so consider exactly R parts, I allow empty parts. If some 2 parts have the number of vertices differing by more than 1, then what I can do is, so if it had one part much bigger than the other part, you can imagine moving one vertex from one part to the other part, and you should convince yourself that this operation should strictly increase the number of edges. Then moving vertices should strictly increase the number of edges of G. And putting this all together, we see that the extremo example necessarily has to be the Turán graph, namely a complete R-partite graph where all the parts have the same size up to almost 1 difference. Okay, great. Any questions? Yep.
Can the Zhao symmetrization technique be used for any other type of problem?
Yeah, so the question is, can the Zhao symmetrization technique be used for any other types of problem? I do have something else in mind, but I don't want to discuss it now. Any more questions? Great. And you see that in both proofs, if you look at this proof as well, you see that the Turán graph is the unique extremizer. I want to give you a third proof that has a somewhat different flavor. So these 2 proofs, they're both somewhat combinatorial in flavor. So I'm doing some arguments, either looking at in this case, picking a clique and arguing what happens outside of it, and over there, again, looking at a maximal example. But the third proof I want to show is more of a probabilistic proof. So this highlights an important method in combinatorics known as the probabilistic method, where we start with a problem that comes with no randomness, but we introduce some randomness to make the problem amenable. And it's a very pretty idea. So we start again with G being an n-uniform, so n vertex k sub r plus 1 free graph on m edges. And what I want to do is to randomly sort the vertex set. So consider a random ordering of the vertices. So I put all the vertices on a line, where the vertices are chosen in random order, and you see some of the edges like that. Let me show you how to find a clique. And essentially, we do it in a not so smart way. Namely, I basically pick all the vertices in some greedy-like manner where I include the vertex in my set if it is adjacent to all earlier vertices. So if all of its neighbors, so I include V if V is the earliest vertex among its neighbors. Okay, so earliest means the leftmost. So if I go from left to right. So in this case up here, okay, so I look at the first vertex. Well, the first vertex should always be in your set. So this vertex, so it has one neighbor, it's to the right, so that's okay. And hold on, that's not what I want to do. So I actually do mean what I was going to write down initially. So if V is adjacent to all the earlier vertices in its ordering. Okay. All right. So, for example, this vertex, it's okay. And I'm also going to include this vertex here because it has both of its earlier vertices both the earlier vertices are adjacent to the third vertex, and I think that's it. Now, this set X, I claim two things. One, that X has to be a clique. So I claim that X has to be a clique because every vertex in X is adjacent to all of the earlier vertices. In particular, all the vertices in X are joined to each other. On the other hand, how big is X, at least in expectation? So for every vertex, I want to understand the probability that this V is included in X. Right, so V has a bunch of non-neighbors, and the property of V being included in X is that all of its non-neighbors appear after V. So the probability that V, little v, is in the set X is equal to the probability that V appears before all its non-neighbors all V and its non-neighbors, they're sorted uniformly, so the probability that this occurs is exactly 1 over 1 plus the number of non-neighbors, which is n minus the degree of V. Okay. But we know that this graph G has no cliques of size r plus 1. So if we consider the expected number of the size of X, on one hand, it is at most r, because G is case of r plus 1 free. On the other hand, by linearity of expectations, right, each vertex is included with some probability, so the size of X in expectation is just the sum of all of these individual inclusion probabilities, which individually we've computed above. Like that. Now, by convexity, I can conclude that this quantity, the sum here, is at least the quantity that would have been obtained if all the degrees were equal to each other. And if you rearrange this equation, this inequality, we obtain that an m is at most 1 minus 1 over r times n squared over 2. And if you compare this number to the number of edges in the Turán graph, okay, so you see that this is basically the number of edges, and this gives you a proof if n is divisible by r, and in fact the number of edges in the Turán graph is exactly this number here if this divisibility condition is true. If it's not, you need to do a little bit more work, because we were a little bit lossy at this step. Right? So you should see that this quantity here is minimized when all the degrees are roughly equal to each other, and you make them as close to each other as possible. Okay, so with a little bit more work, you can get the exact version of Turán's theorem up there, but at least what we've shown is, so from here, we've shown that the number of edges is at most this quantity, which for most purposes is basically as good as Turán's theorem. Okay, any questions about this proof here? And so it's a probabilistic method proof. So we're introducing some randomness into the problem that originally had no randomness in it. Okay, great. So let's take a very quick 2-minute break. And then when we come back, I want to show you that even though we've shown so many different proofs of Turán's theorem, Mantel's theorem, you might think, okay, this is a pretty simple thing. Even if I tweak the problem just a little bit, there are so many things that we do not understand, and many important open problems in combinatorics that are variants of Turán's theorem. So let's take a quick break. Okay. So far we've been talking about Turán's theorem, or generally the problem of if you forbid a certain structure, forbid a certain subgraph, what is the maximum number of edges? We're going to spend the next few lectures discussing more problems of that form, and it turns out, for the questions that the answers we've just seen, they're deceptively simple, and for almost any other situation, we don't really know the exact answer. And for many questions, we don't know anything close to the truth. Right? And in particular, I want to show you one variant of this problem, namely what happens instead of looking at graphs, if you look at hypergraphs. And that's a major open problem in combinatorics, what the truth should be. So here is an open problem which is what happens to Turán's theorem for 3 uniform hypergraphs. Okay, so don't be scared by the word hypergraph. So whereas you think of graphs as having edges consisting of pairs of vertices, a hypergraph is simply a structure where, well, for 3 uniform hypergraph, the edges are triples of vertices. Okay. So question is, what is the maximum number of triples in a graph, in a 3 uniform hypergraph without, well, for Mantel's theorem, we asked what happens without a triangle. For 3 uniform, the basic question you can ask is, what about forbidding a tetrahedron? So suppose you don't have four vertices, such that every triple inside the 4 vertices is an edge. What's the maximum number of edges you can have in an n-vertex 3 uniform hypergraph? Already, it's not so easy to come up with good examples. So Turán's theorem says take a bipartite graph, complete bipartite graph. Well, here, it's not so easy to come up with examples, but there are some examples. And in fact, Turán suggested the following construction. Namely, you divide the set of vertices as before to 3 roughly equal sized parts. And let me take all triples that look like one of the following forms. Either 3 vertices, 1 in each vertex set, or a triple looking like that. 2 vertex in one set, 1 in the next set, or going cyclically like that. Okay, so I include all triples with one of these forms. And you should check that this construction has no tetrahedron. Okay? If it had a tetrahedron, it would have had at least 2 vertices in one part, also then where the other 2 vertices can be. Okay? So you can check that it cannot happen. So then how many edges does it have? So the exact number is not so important, but what's important is that the edge density, so of all the possible triples, the fraction of edges that are contained in this construction is 5/9. And it is conjectured that this is optimal. However, we're quite far from proving this number. So the best upper bound that is currently available, and it's found quite recently using this fairly new method in graph theory called flag algebras, essentially a computerized way to try to prove such inequalities. And the best upper bound is something like 0.562. And it's a major open problem to either prove or disprove that this construction here is the optimal one. So you see, even though I presented so many proofs of Mantel's theorem and Turán's theorem at this point, hopefully they should all be, they seem quite simple in retrospect. It's deceptive. It's deceptive. And even if I change and tweak the problem just a little bit, going to 3 uniform hypergraphs instead of graphs, we really have no idea what's going on. Yes, question?
Maybe say, why do you say it's this is really bad compared to true? This doesn't seem like that big a difference.
Okay, so great. So the question is, why do I say it's a pretty big gap? So we know that there has to be some proportion of the total number of triples. Right? So, well, you have two numbers, and well, they seem. I mean, to me, they seem pretty far apart. It's not some lower order gap. Right? So this is a first order gap. Okay. Any more questions? But it's true that later in the course we'll see gaps that are much bigger. We'll see gaps where it is like a polynomial on one side and like a tower of exponentials on the other side. And there, I agree, that's much worse. Right? So the gap is much bigger. Here, it's just two numbers, but in the worst case, there can be two numbers anyway. Any more questions? Okay, so throughout this course, I'll try to bring out some open problems, and there are lots. Right? So I'll tell you what we do understand, but most things we do not understand. And hopefully, some of you will go and try to understand them better. So the next time I teach the course, I can have something new to present. Okay. So now that we've addressed the question of what's the maximum number of edges if you forbid a triangle or a clique, the next natural thing to ask is, what about if you forbid a general H? So give me a graph H, and what's the maximum number of edges if you forbid that H? It will be helpful to introduce some notation. So the extremal number, which we'll denote by EX, and this is also called the Turán number, sometimes because of Turán's theorem. So we'll probably call it the extremal number more frequently. So this number here is defined to be the maximum number of edges in an n-vertex graph containing no copy of H as a subgraph. I want to just clarify a piece of notation. So when I say a subgraph, so what do I mean? So there are several notions of different kinds of subgraphs, and the couple that come up somewhat frequently, one is subgraph, and then there's something called induced subgraph. So probably easiest if I just show you an example. So suppose my H is the fourth cycle. So an example of H being a subgraph is, well, suppose I have this graph here. So H is a subgraph of this graph here, or in many different ways, but in particular like that. But you see there are some more edges that are among the vertices, but that's okay. So subgraph only requires you to have a subset of vertices and a subset of edges. Whereas induced subgraphs, this is not an example of induced subgraph. And so induced subgraph means that you take the set of vertices and you look at all the edges in the big graph among your set of vertices. So that's an induced subgraph. So here, the fourth cycle is an induced subgraph, but not induced subgraph over here. Okay, so I just want to make that distinction clear. And for now, in this chapter, we'll only talk about subgraphs, right? So not induced necessarily. All right, so let's recap what happened for Turán's theorem. So Turán's theorem told us that the extremal number of these cliques, well, we know very precisely to be the number of edges in the Turán graph. And well, in particular, we saw from the last proof, but also similarly, if you just do a calculation, that it is at most this quantity over here. And it's basically that quantity. So you can, so the number of edges in this Turán graph is asymptotically that quantity up to a lower order error if you let n go to infinity for r fixed. And the basic question is, what about general h? So if I give you some arbitrary graph h, what can you tell me about the maximum number of edges in the graph, forbidding this h as a subgraph? And it turns out for most h's, we have a pretty good understanding. And perhaps quite surprisingly, because you can imagine this problem looks like it might get quite complicated. Right? All the proofs that we've done are very specific to cliques. But it turns out that we already understand a lot. And the critical parameter that governs how this quantity behaves is the chromatic number of h. Right, so if you tell me the chromatic number of h, I can already tell you quite a lot. So just to remind you, the chromatic number of a graph is the minimum number of colors you need to properly color this graph. So the chromatic number of h, denoted chi of h, is the minimum number of colors needed to color the vertices of h so that no two adjacent vertices have the same color. Okay, so for instance, if I give you a clique r plus 1 vertices, okay, so all the vertices must receive different colors because every pair of vertices is adjacent. So the chromatic number is r plus 1. Okay, the chromatic number of the Turán graph is what? It's r. Right? So the chromatic number of the Turán graph is r. I can color each part in this complete bipartite graph using a different color, and that's the best I can do. Now, if I have one graph being a subgraph of another graph, what can you tell me about the relationships between their chromatic numbers? So if h is a subgraph of G, so what can you tell me about relationship between their chromatic numbers?
The chi of h is less than or equal to chi of h.
So okay, you're telling me that the chi of h is at most chi of G, and why is that?
Because if G can be colored with a certain number of colors, then that also automatically contains a valid coloring.
Great. Whatever coloring you do for G, you use the same coloring, and that's a proper coloring for H as well. So the chromatic number of H might be smaller, but certainly cannot be bigger than that of G. So in particular, if you have a graph H with chromatic number r plus 1, then this Turán graph is always H-free. So if H requires 4 colors, it cannot be embedded into the complete multi-partite graph on 3 parts. So the Turán graph is also an example of an H-free graph with lots of edges. And this tells us that the extremal number of H is at least that of this Turán number, where R is defined as the chromatic number minus 1. Okay, so that's some lower bound construction. So as we saw earlier, we know what the asymptotic is like for the number of edges as n goes to infinity. Namely, it's like that. And now the question is this the right answer? Is it possible that we completely missed some construction that might produce a lot more edges? And it turns out, and I think this should be somewhat surprising because so far I feel like I haven't really told you anything that's surprising yet. Seems like a fairly mysterious problem, but it turns out that this is more or less the right answer. So you cannot do much better than the Turán graph. And there's the theorem of Erdős-Stone-Simonovits that for every graph H, okay, so if I fix H, then the limit as n goes to infinity of the extremal number as a fraction of total number of pairs. So here, this is the edge density. So this quantity here is equal to 1 minus chi of h. So 1 minus 1 over chi of h minus 1. So knowing the chromatic number, in some sense, completely determines how big the extremal number should be. And you see that so far everything we've proved, Turán's theorem, Mantel's theorem, agree with this formula here. But if I give you some h, maybe quite complicated, and those previous proofs don't work, but still you know the first order asymptotics. Well, okay, but there's still more to say. But first, let me just run through some examples for sanity check. So if H is a triangle, so H, chromatic number, and this limit. So if H is the triangle, chromatic number is 3. Okay, so then this limit is 1/2. And that's indeed the case. So that's what we did with Mantel's theorem. If H is a clique on 4 vertices, then the chromatic number is 4. And the answer is 2/3. And also that agrees with Turán's theorem. Yeah, agrees with Turán's theorem. But I can give you some fairly complicated looking H. So for example, H might be the Peterson graph. So every good graph theory course should feature a Peterson graph at least once, somewhere. So that's the Peterson graph. What's the chromatic number of the Peterson graph? Actually, that's kind of a tricky question. The last time I taught this course, I even got the answer wrong. So it turns out you can 3-color the Peterson graph. Okay, so it's completely not obvious how to do this. But if you, well, there are only so many vertices. If you stir it long enough, you can see what happens. But let me just show you a 3-coloring of the Peterson graph. Right, and the 3rd color is like that. Okay, so that's a 3-coloring of the Peterson graph. That's chromatic number 3. It's not 2. Okay, so why is it not 2? It's not bipartite. It's a 5-cycle, which cannot be 2-colored. Right, so then the limit is 1/2. And no, 3. Yeah, great. Yeah, so the limit is 1/2. And here we can apply this theorem as Erdős-Stone-Simonovits. And I think it should be somewhat surprising, right? Because the Peterson graph looks quite complicated. If you try to forbid this graph in some big G, it seems like it's kind of hard to do. But it turns out the chromatic number completely governs the behavior of the extremal numbers. But it turns out that's not the entire story. Because, well, this is quite a good theorem, and I said it gives you the first order asymptotics. Actually, that's a lie. It doesn't always give you the first order asymptotics. And when is Erdős-Stone-Simonovits not effective? Or rather, it's not the complete, somehow not the final answer. Well, you can say, what about this little o? Okay, so that, right, so we're still trying to understand, there's a limit, and you can understand what is the, how quickly does it converge to this number here? Okay, so that's certainly a valid question. But more importantly, though, if your graph is bipartite, if chi of h equals to 2, i.e. bipartite, then all this theorem tells you is that the limit is equal to 0, which somehow is not the most satisfying answer. You want to know the first order asymptotics. I mean, this still tells you something. So the Erdős-Stone-Simonovits theorem tells you that the extremal number is little o of n squared. But of course, you are a curious mathematician and you want to know really what is the asymptotics. Is it like n to the 3/2? Is it like n to the 4/3? What is it? This is not satisfying. And it turns out for most bipartite graphs H, it is a very difficult problem that we still do not know the answer to, even what is the order of the asymptotics. So the next few lectures, what I want to do is to show you some techniques that will allow you to prove some upper bounds for this extremal number in the case when H is bipartite that shows you that the exponent can be less than 2. And I will also show you some constructions that sometimes, but in a very few cases, matches the upper bound. So there are very few examples of graphs H for which we know the first order asymptotics. And for most graph H, they are major open problems in combinatorics. And there's some really old ones for which any solution might be quite exciting. I will not show you a proof of Erdős-Stone-Simonovits now. We will see that later in the term once we've developed some more machinery. Although, later on in the term, we'll see a proof using the so-called Semiradis regularity lemma, which I've mentioned a few times in the first lecture. Although you don't actually need such heavy machinery. So there is, the original proofs of Erdős and Stone, and also by Simonovits. So Erdős and Stone first proved this result for H being a complete multipartite graph, and Simonovits observed that knowing H for a complete multipartite graph actually implies this result in general. So you will not find a paper with all three of them in being authors. But this is what the theorem is called. So later on in the course, once we've developed the machinery of graph regularity lemmas, I will show you how you can deduce Erdős-Stone-Simonovits from Turán's theorem. So somehow you use Turán's theorem and bootstrap it to Erdős-Stone-Simonovits. Right, so that should seem somewhat magical. Right? So on one hand, you have cliques. On the other hand, you have things that somehow don't have cliques in them. Right? They don't really look like cliques, but you can still bootstrap one to the other. And so after we develop some machinery, we'll do that. But there is a combinatorial proof which doesn't use any of this heavy machinery. So I won't discuss it in lecture, but you can look it up. And it's quite nice. It has some combinatorial techniques and some double counting arguments. I want to, so going forward, I want to show you some questions, mostly questions, but some answers as well. So questions such as, what is the extremal number of, so what are some of the basic bipartite graphs? One of them is just a complete bipartite graph. So this has a name, it's called the Zirankiewicz problem. And for some values of S and T, we know the answer, but for most values, we have no idea what the answer is. For example, for K44, we do not know what is the correct exponent on the n. So even fairly small cases, it is very much open. So this is all to show you that these simple proofs that we did today, they are perhaps too deceptively simple. So even if you change the question a little bit, we don't understand a lot. So questions like these will occupy the next several lectures, and I also show you some constructions, and there's some constructions that use nice algebraic ideas and some probabilistic ideas. So we'll have C ideas coming from many different sources. I want to close off by just a cultural remark. So in this course, especially the first half, we'll encounter a lot of Hungarian names. So we already saw a couple of them. And I just want to give you a very quick tutorial on how to pronounce Hungarian names, because just for cultural purposes. Now, in the past when I taught this class, there were no Hungarian speakers, but I think we do have at least one Hungarian speaker in the room, so I want to, but you are a native Hungarian speaker, right? So you should tell us, okay, so can you help us pronounce these names? Erdős. And this one? Okay, so it is Hungarian, Simonovits. Right? Yeah. So the one, I'll just tell you two things about Hungarian names. One of them is that the S is pronounced like sh. And another thing that comes up is SZ, which we saw in Semiradi. So this is pronounced like S. Forget the Z. Okay, so Erdős. Another thing about Erdős that you should know is that what is this accent? It is not a double dot. So in LaTeX, you would type it as /H. And in particular, not like that. Okay, so just a few cultural remarks about names. Okay, great. So we'll end today, and then next time we'll start looking at other extremal numbers for more bipartite graphs.